Okay, good morning. So it is my great pleasure to come here to this summer school that I can share some background knowledge and some progresses and also some exercise on the topic of transfer learning. So I believe most of you have some backgrounds on vision and learning, right? So today we will probably not go into very details for like each algorithm, each particular application. Instead, we will highlight what are the topics, applications, or the trends in the direction of transfer learning, and especially with application to computer vision. Okay, so I think I'm still supposed to speak in English, right? Okay, 但是讲笑话还是可以用中文啦，可以吗？ Or you can still ask questions in Chinese. It's totally fine. Okay, we still can do QA in Chinese. 还是可以用中文发问，还是可以随时举手发问。But I think for the record, I still need to give this lecture in English. Or you can feel free to stop by during the breaks if you want to ask any questions in private. That is totally fine. Okay. 虽然我不大会讲笑话。Okay, so like Professor Chiang said, I graduated from CMU in 2009, and after that, I came back to Taiwan and joined Academia Sinica from 2009 to 2017. Starting last year, I joined NTU in the EE department, and as you can see, my research focuses are computer vision, machine learning, image processing, pattern recognition, etc. Okay, and as you can imagine, computer vision is a very application-oriented research area. So for me, not only myself, for my lab, my students in my lab, we are not only like writing papers, trying to publish papers only at either Academia Sinica or National Taiwan Universities. We also work closely with industries like TSMC. Well, although there is some bad news from TSMC recently, but we have nothing to do with that. Okay, but we do have an intern working at TSMC right now. So anyway, so and E3 and other startup companies as well. So we not only write papers, we also work closely with the industries because we want to know what are the really topics of interest, not only from those top conferences, but also from the real applications. So that is why we try to do both, not only at Academia Sinica, but also in National Taiwan Universities. Okay. I probably should ask my student whether or not he brings his own USB into TSMC. Okay, anyway. By the way, so this lecture is recorded, so I need to speak carefully. Okay, so let's get back to the main topic today, transfer learning. So if you take courses on machine learning, computer vision, or if you work in related areas, you probably hear of the term of transfer learning. But in case you have not, it is okay because like in the first 30 minutes or so, I will highlight the idea of transfer learning and let you know why this is among recent popular directions in computer vision or machine learning. But of course, for other lecturers of these summer schools, they are all very interesting topics, which you should really pay attention to. Anyway, you still pay for the registration fee, right? Okay, so let's start from the introduction of transfer learning. Well, since most of you have backgrounds in computer vision, machine learning, and hopefully deep learning, you probably know we already have great progresses on deep learning, right? For example, like big name companies, Facebook, Google, they already have very, very powerful tool, very powerful algorithm for face recognition. So they can do face recognition much better than humans do in nowadays, right? But why are they able to do so? Well, because they are big name companies. They are very well established companies. So they have tons of images, tons of face images from millions, trillions of users. And that is why they have many training data, and hopefully those training data have ground truth labels, and they will be able to train their powerful deep learning algorithms, and that is the reason why they are able to do better than humans in terms of face recognition. So it is not surprising that for the supervised learning part, deep learning, we already see very, very successful applications results for the supervised part of deep learning. Okay, but what are the next things to do? What are the next things to pursue in deep learning? Well, not just me. Well, there are lots of big name guys. They also agree that transfer learning is among the next things to explore. So like Andrew said, transfer learning will be the next drive for machine learning. And from this plot, you can see that the horizontal axis indicates the time, the years, right? So you can see around this time of the year, or even like 1 or 2 years ago, we already see the big boost of deep learning, especially for the supervised part. And the next things we are going to look at, and including those big name people, they will look at transfer learning, unsupervised learning, and reinforcement learning. Okay, so today we only have like 3 lectures today, right? So only focus on the part of transfer learning. So again, I will let you know why we are looking at transfer learning and what are the opportunities here. Okay. Well, like we see in the previous slide, it is not surprising we already have great successful applications for supervised part of deep learning. And the reason for that, like I mentioned a few minutes ago, because we have tons of data, right? And those data, we probably have ground truth labels. In those cases, we will be able to train our deep learning algorithms, deep learning models, and make things happen. But what about in the real world scenarios? Think about that if you are a startup company. You have a very, very good idea, very, very good solution. You try to make your company happen. But you just start your own company. You probably don't have like thousands of users for your company, right? So in that case, you probably will not be able to collect a large amount of data. You probably not be able to collect a large amount of labeled data. In that case, you do have problems in this part, collecting labeled data. Without that, you probably will not be able to train your deep learning algorithms to make your deep learning models happen. So I think transfer learning comes to the rescue. We try to fix, or we try to alleviate this data-oriented problem when we want to train our deep learning models. So we gradually look into the real-world scenarios and explain why deep learning plus transfer learning would be very important for many of you. Not all of you. We'll get back to this in a few minutes. Okay, so let's see what's the definition of transfer learning. In case you haven't worked on this topic, I think most of us would do is go to Google, go to Wikipedia, and search for the definition of transfer learning. And you can see there are sentences here you probably will fall asleep. But anyway, from the results of Wikipedia, you probably still cannot tell what do we really mean by transfer learning and what we really want to do for this research direction. Okay, so let me give you some examples first, and maybe it is easier for you to get into this area. Like this, I always like to show this example. There are 2 different kinds of sports, right? One is table tennis. The other is tennis. Okay, this sounds familiar because of their English name, but in terms of Chinese, they are very different, right? But anyway, the point is not the name of their the type of the sports. What I meant is here, for these 2 different kinds of sports, they do exist commonly shared techniques. How to serve the ball, how to return the ball, or even like some rules, there are some features which are shared by both kinds of sports, right? So if you play one sport well, probably you can do not bad in the other. So this is a very starting example of transfer learning. It looks like they are totally different, irrelevant things, irrelevant data domains, but if you do well in one domain, you probably want to see if you are able to do equally well in the other. So that is a starting example of transfer learning, okay? And the next thing is this. Imagine that you are an engineer of Boeing or Airbus. Anyway, I do like airplanes from both industries. But anyway, if you are an aviation engineer and you do want to make an airplane fly, what would you do? Well, it probably makes sense to see how the birds fly first, right? Before making an airplane fly, you do not know what to do, then you go back to other data domains. You want to see, well, I do see birds fly, and can we learn anything from the birds so that later, when I build up my own airplane, I can make it fly as well. Okay, as a good engineer, you probably would know what are the things make the bird or the airplane fly. Is it because we have the feather on the wings? Probably not, right? Is it because the wings can clap so we can make the airplane or make the birds fly? Probably not either, right? The thing that's really important, which is shared by both data domains, it is like some physics, some 流体动力学是什么？我不知道那个是英文是什么 ，so sorry about that. Those are the things which are commonly shared by both data domains. That is why you can look at the data in one domain. You can try to learn this information from one domain, and eventually you can do well in the other. And the so-called the other domain, that is the domain really of interest. And later we will use the term the source domain. And this would be the target domain. The target domain is the really domain of interest. So later in this lecture, we will use these two terms when we talk about transfer learning, domain adaptation, these kind of things. Okay. So we are all good so far, right? 我很怕讲英文会让大家睡着。Okay. So let's get back to some engineering examples. Those are some starting examples. So let's get back to the computer science, machine learning parts, examples of transfer learning. Well, I think it is not surprising that many of us will be working on semantics analysis in the future. What do we mean by semantics analysis? Well, take this as an example. We want to look at a paragraph and determine whether it is a positive one or a negative one. Okay, it is commonly that we need to do that for the movies, for the books, for any other kinds of the products. Okay, but like I said in the very beginning, imagine that you are a startup company. For example, you want to sell DVDs. But the only thing you can get is like the information from 博客来 or other online bookstores. So in those cases, will you be able to look at the information from those online bookstores? And you can learn the information, learn the semantics information from that part. And eventually, because you are selling DVDs anyway, you still want to determine whether or not when a user leaves some feedback, leaves some sentences on your website, it is a positive one or a negative one. But again, you can imagine that because these are two different kinds of data. One is describing the books, and the other is describing the movies. So the content information is different. But there must be some commonly shared features. You will hear these terms quite a lot today. We have some commonly shared information, commonly shared features across these two domains. And again, if you are a startup company selling DVDs, selling TV series online, you probably will be able to, you probably want to borrow the information from other websites, from other places, so that you still can do a very good job in recommending or making comments for the DVDs you are going to sell, so that the user will have a better idea whether or not he will like this movie, or whether or not this movie is really attractive to him or her. Okay? And the next example, not only the vision, the text part, speech as well, sounds as well. If you accidentally, or sometimes you just have some song in mind, you just barely remember the melody. You really want to know, can you like sing a short part of it? Then the machine, the computer, can retrieve the proper song. It can identify the singer from the melody you just sent to the machine, right? But you can imagine not all of us like Ame or Zhou Jielong or whatever. So the sound we make will definitely not the same as those of these wonderful singers. So again, there is a domain difference. Later we will also use this term a lot, domain difference. There is a big domain gap between these two data domains. So whether or not we can make our algorithms learn the features, learn the information from the source domain, and eventually we can do information retrieval. We can search things from the data in the other domain. So that is also another example. Well, medical imaging. This is also among the research, the recent interest of many people. When we do medical imaging, sometimes we want to identify, or we want to recognize whether or not a CT image or an MR image, there is a tumor in it, or whether or not there is a broken bone, etc. But what happens in real life is usually it is a highly imbalanced setting. What do we mean by imbalance? You can imagine there will be lots and lots of image data of normal type. For the normal images, we will have like thousands of images, but for the tumor ones, we do not have as many, right? So in that case, can we go to other domains, for the medical images of other organs or of other sensors? Can we borrow the information from other parts so that we can alleviate the imbalanced setting? So in that case, we also want to alleviate the domain gap between two data domains. Again, that is like, this is CT, I believe. Eventually, we want to do image classification using CT images, 电脑断层. Okay, but like I said, we probably do not have lots of like the images corresponding to breathing, broken bones, or a tumor for the CT images. So we want to do this kind of transfer learning, and in that case, we can alleviate the domain difference and also alleviate the problem of imbalanced learning. Okay. I hope that we have already provided a sufficient amount of examples trying to let you get into the idea why we need to work on transfer learning. But I can give you one more example. I think this is also very close to real life application, or at least close to what many people are talking about nowadays, the self-driving car. Okay, for the self-driving car, for computer vision people, what we want to do is design a good segmenter, image segmenting model, or you can say semantic segmentation. Like taking a picture of a roadside scene. We want our model to be able to identify where the road is, where the cars are, where the buildings are, 或甚至哪里有三宝之类的. But anyway, this is the data, like for example, from Frankfurt, from one city in Europe. But imagine that, I hope that you will be the boss of BMW, Benz, or whatever. You can imagine that when you build a very, very good self-driving car, you not only want to sell your car only in Germany, right? You probably want to sell your car to other parts of the world. But in that case, are you able to say, yes, I'm very, very confident I will sell my cars to other cities in the world, and I still can do a very good job in identifying the road scenes in other cities? You probably are not that confident, right? And what is the reason? Because the composition of the roadside scenes are very, very unique for each city in the world. But like I said, if you are the boss of BMW or if you are the boss of Benz, what you don't want to do is, for example, you want to sell your car to Taipei, then you need to hire like thousands of people, thousands of labor trying to collect the data and also annotate the data for you to train a Taipei-specific segmenting model. You probably do not want to do this, right? Because it takes a lot of money to hire lots of labors. 我们最低基本工资要调嘛，对不对？ Anyway, but it takes a lot of time to do so as well. And you probably do not want to do that for each city in the world. So how can we transfer the idea? How can we transfer the information you learn from one city? And eventually, you can sell your self-driving cars to other cities in the world. And that is the point. So that is also a very, very practical computer vision example related to transfer learning. So actually, I worked with Sun Ming's lab last year, and we do have some results on this part. And later, I believe this should be the second part of this lecture. I will also highlight how we maybe not solve this problem entirely, but at least we alleviate these transfer learning problems for self-driving cars. Okay. So what really happens right now is, like in Silicon Valley or in some big name companies in US, although they do have self-driving cars driving around in California or in other places in the world, they are looking at collecting more data to alleviate the problem. So what they do is, well, they just go to collect synthetic data. For video games, I believe you will be able to synthesize whatever road scene composition you want. You can synthesize whatever weather conditions you want, right? So in that case, you will be able to collect a large amount of training data to train your segmenting models. But I think both you and I will agree that it doesn't matter how realistic, how practical these images look like. Fundamentally, there is still a domain gap. There is still a domain difference between synthetic data and real-life data, right? So although you will be able to collect tons of training images, although you can collect tons of annotated training images using video games, but eventually you still need to address the problem, how to alleviate, how to take out the domain gap so that you can put all the things together to train your segmenting model. So that is what really happens currently, one of the possible solutions. Okay. So like I said, having seen those examples, you will probably have a much, much better idea why we need to look at transfer learning, because we don't want to collect a large amount of data each time for each topic, because it is very time consuming. It costs your company a lot of money, and you don't want to do this. So that is why we want to go beyond the techniques, the ideas of traditional machine learning, and look at the direction of transfer learning. Okay. But of course, later in the second part or in the third part of this lecture, we'll look at the examples not only focusing on the classification part. We will also show you some directions, some topics, some examples in image synthesis, image translation, like style transfer. Those can be considered as successful examples of transfer learning as well. Because for style transfer, you want to convert the style of your image into the image of another type of style, right? So essentially, you are still communicating the style information across two data domains. So image synthesis, image manipulation, it can be also considered as the example of transfer learning. Okay. So now we can ignore those lengthy definition of transfer learning because I show you a lot of examples and you already have a very, very good idea what the transfer learning is and why it is important and practical for many, many examples. And like we just looked at the definition or in the previous examples, you understand why we want to get rid of the basic assumption in machine learning. We want to go beyond what the standard machine learning can do. We do not want to assume that the test data will come from the same, or I should say, we don't want to assume that both training and test data will have similar data distribution, those kind of things. Like we just said, the test data might be in another data domain of interest, and many, many times we need to borrow the training data from a totally different source domain. And how can we do the machine learning algorithms in this kind of scenario? And that is what we really care about in transfer learning. Okay. So because I think many of you, I look at your registration data, so I think many of you have taken courses in machine learning or have some backgrounds. So I believe the definition I just gave you should be efficient. But again, in case you have any questions, if you are not clear what I am talking about, please feel free to interrupt me or just raise your hand or do whatever you want to do to catch my attention, okay? And let me know if you have any questions. All right, so this is what I just talked about. We want to get rid of the domain gap between training and test data. And eventually, we don't want to overfit our training data, but at the same time, we still want to have our model generalized to the test data in a different domain. That is the purpose of transfer learning. Okay. So in case some of you know, there is still a small amount of people in this class who have not taken vision or learning classes. In case there are still some of you are of this type, I can give one last example. So imagine that you are sitting in the computer vision classroom. So in homework 1, let's say your lecturer, your professor asks you to do face recognition for recognizing all the students in your class. So what would you do in homework 1? You probably will go out to collect all the face images of your classmates, right? And not only that, what you need to do as well, you need to annotate your data. You need to annotate the identity of the face images you collected, right? So that is what you need to do to collect the data for homework 1. After collecting such data, you will be able to design your algorithms, whether or not your professor asks you to do PCA, SVM, or any other kinds of classifiers. You can do homework 1. So eventually, after 2 weeks, you finally finish the homework. You got A+. You are very, very happy. What about the next homework? What if your professor asks you to do expression recognition of face images? Again, you need to do that from your classmates. Would you be a little bit pissed because you would say, why don't you tell me earlier, professor? If you tell me earlier, when I collect the face images of my classmates, I will not only annotate the identity information, what I will do as well, I will also write down what expression it is. I will also annotate the expression ground truth information. In that case, I don't need to do data collection and annotation all over again, right? But anyway, you need the credits, so you still collect the data. You still need to do homework too, and eventually you got A+. Again, hopefully. Okay. Well, you would think your professor would move on, but eventually, unfortunately, he or she asks you to do gender classification for homework 3. Now you are really mad. Well, maybe not as mad as homework 2, but anyway, you need to give the label for your face images again, right? So that is what I said. If you are not using transfer learning techniques for each topic, for each application, you always need to do data collection. You always need to do data annotation before you can train your model. Okay, but with transfer learning, like the face examples I just gave you, well, face images are faces anyway, right? So there must be some commonly shared features that can describe the face images. Maybe some part of the feature, maybe some dimensions, some attributes are better in describing the expression. Maybe some attributes, maybe some dimensions are preferable in recognizing the gender. But anyway, face features are face features. There must be some commonly shared information you can borrow from the first 2 homeworks, so that for the third one, you probably still need to annotate the data, but probably not the entire class for this data annotation process. So that will alleviate your data collection or data annotation efforts when you solve such face-related applications. Okay. So again, this is a classification example for transfer learning, or later we will use the term domain adaptation. But anyway, I hope this gives you another example related to face recognition, why it is a good idea to learn about transfer learning, to have some ideas about transfer learning. And don't worry, in the last part of this lecture, we will also have 2 TAs assigning some exercise for you to practice. But of course, we are not working on face recognition. We will start from the very, very simple ones to do like digit recognition. And in the last part from 4 o'clock or so, so we will work on the examples of digit recognition using different types of handwritten digit data. Then you will get a better idea how to design transfer learning algorithms so that you can train from one data and you can do recognition on the other. So we'll see that in the last part today. Okay. So I have a table summarizing the definition, the settings, but I think it would be probably a little bit too early to look at this part. So anyway, so we will, when we introduce different kinds of algorithms, we will look into what do we mean by source and target domains. They are the same type of data, same type of features or not. As for the task of interest, they are the same or not, etc. We will look into this later. I think it is better for you, easier for you to understand. All right. So again, we are all good so far? Okay. So before we move on, there are 2 things I really want to to have you think about. The first thing is transfer learning. We really need to pay attention to either the algorithm or the purpose we want to achieve when we look at this direction. Because the basic idea, the essential idea of transfer learning is that we want to learn by analogy. And hopefully, what do we mean by learn from analogy? And that is why in the previous slide, I mentioned that whether or not the source and target domain data, they are the same, even if they are different, they must be related. Remember that in the very, very first example I just gave you, there are 2 types of sports, right? Table tennis and tennis. So there are different kinds of sports, but they are related. They are relevant. Okay. So depending on the data of interest, depending on the task of interest, we really need to pay attention and see if we are able to generalize the learned information, the learned features, or the learned model from one domain to another. We really want to do the so-called 举一反三, but not 东施效颦, these kind of things. But again, we'll look into some examples later. Another thing what I want you to think about is whether or not we really need to know transfer learning. Well, if the answer is no, you probably can skip the class today, right? But anyway, the point is not that because you already pay your tuition fee. But anyway, but that is not the main reason. The main reason is that you need to think about what kind of examples I just gave you in the past 20 minutes or so. What motivations I just gave you for the first 20 minutes or so. I kept saying that if you have some particular application of interest, if you have particular data of interest, but you are not able to collect a sufficient amount of data, if you are not able to collect a sufficient amount of label information, ground truth information for your data of interest, then you need to look into transfer learning. And that probably applies for most companies, for most startups, etc. But if you are working in a big name company, a well-established ones, you already have like trillions of users. You have lots and lots of data. And the users will give you the annotation. You don't need to hire people to do the annotation by yourself, right? So in those cases, in those few particular cases, you probably don't need to worry about transfer learning because you already have a very, very large amount of data with large and intra-class variations, and you also have the ground truth information. So in that case, you probably don't need to worry about where to borrow the information, where to borrow the feature, which data should be your source domain data. You already have tons of data to train your learning algorithms. For those cases, you probably do not need to worry about the problem of transfer learning. But again, for most of you, if you work on a particular application, if you are the engineer or the owner of the startup companies, you do not have as much data as you want, then you need to you need to think about the transfer learning part. So hopefully, you will still be happy to sit here today to learn some things about transfer learning and to do some exercise for it. Okay, so later I can show you some even more interesting examples of transfer learning. Okay, they are not purely like image classification or semantics segmentation, semantics analysis, those things I just mentioned. There are things that go beyond classification or go beyond standard image classification, and you can consider them as examples of transfer learning as well. Okay, so the first one is continuous adaptation or continuous transfer. What do I mean by that? This is one of the examples. And you can see that the horizontal axis indicates the time of a day, right? And you can see that this is the same image captured by a surveillance camera. So the idea here is if I show you some example of the same images with the time ground truth information, we'll be able to predict how the images would look like at different times of a day. So you need to transfer the information from your training data to the to different times of a day. And those times you may or you may not have the training data. You may not see this data in advance. So in that case, those are your source domain images. And in these different times of a day, they are your target domains. Whether or not you can transfer the information from source to target domain, this is one of the image translation or image manipulation examples of transfer learning. Okay, and you can imagine that in this case, we are predicting how a thing would look like at different times of the day, right? So what are the things you want to preserve in your output images? What kind of the things you want to alter? What kind of things you want to manipulate in this different time, in this image of different other times of the day? You need to think about it. You probably want to preserve the content information for these images in different times of the day. What you want to manipulate, what you want to alter is like the lighting condition, the style information for those images in the target domain. So anyway, so this is one of the image manipulation example. You want to alter, you want to manipulate your images while being able to preserve the content information. And this can be considered as one of the example of transfer learning or a style transfer. Okay. But actually, not only computer vision or deep learning people work on this topic. For other areas like computer graphics, they have been working at this example. They probably did not consider the deep learning algorithms for this particular example, but I just want to let you know that there are different kinds of techniques allow you to do so. But anyway, this is one of the examples published a few years ago in SIGGRAPH, and so you can see in computer graphics they do have similar examples. They want to alter the style of a cityscape skyline image. They want to preserve the content information, but at the same time, they want to alter the style, the lighting condition. But the thing is, in this particular example, they want to assume that they do not want to have this kind of particular night images for this particular city in their training example. If they do, then there's no transfer learning problem, right? So in this case, they do have lots of cityscape images, skyline images, daytimes or night times. But for this particular city of interest, I believe this is Singapore, if you have been there. If you, for this particular example, they do not have Singapore, the images of Singapore to be captured in night times. But eventually, what they want to do is, they have the Singapore images to capture during daytime, and they want to predict what it should look like in the nighttime. Okay, so this is one of the examples. Not only different times of a day, some people would do different seasons of a year. They want to alter a summer image into winter or vice versa. But of course, it is usually easier to do from converting the image of a more complex style into a simpler style instead of doing the other way around. Okay, but anyway, style transfer, image manipulation, we are communicating the information across two data domains. And here, style or the lighting condition is the domain, the style of interest here. Okay. Another thing which is, well, somewhat interesting is when people not only look at the city images, they also look at the food. They want to predict different conditions of the food, and they want to see how these images would look like in different conditions. For example, for an apple, for a banana, what does it look like from the original state, or what would it look like if it is sliced, or it is moldy, etc. They want to predict different status, different state of the food images. So you can consider that as transfer examples as well. But again, the thing here is we only have the training images for one particular food, and they want to transfer the information to another. So again, there are lots and lots of interesting things to pursue in terms of image manipulation, style transfer. Okay, so this is probably a very well-known example for some of you, pigs to pigs, image style transfer. The most popular example you probably have seen online is, can you draw a sketch image, then you want your model to automatically convert the image you just draw into a real one, or at least a one close to the real world scenario. So how do you convert the image from sketch to photo? So that is one of the examples. But not only for this, like to do the colorization. Can you convert a grayscale image into color image? Can you convert the semantic segmentation output into a photorealistic image? Those are all style transfer examples, and this can be considered as the examples of transfer learning as well. For example, for this one, we are associating the image domains of sketches and the photos. For this one, we are communicating the images of semantic segmentation outputs and, again, the real-world photos. So we are dealing with the data across two data domains, not only for classification parts, but also for image synthesis, for image manipulation. Okay. This will probably get some of your attention, right? If you have seen the Japanese animation movie last year, you will probably have an idea where this scene comes from. It is in the very last thing. It's in the very last scene in the movie, right? 你的名字, right? So this is also a style transfer example. And you can convert this photo into the so-called 星海乘风, right? So again, this is an example of transfer learning, and I can assure that this is exactly the same image because this photo was taken by me. So early this year, I went to Tokyo and I took this photo. I'm not a big okay. I like the movie. Okay, so I went to this scene to take this photo, and I later found out an interesting app online or in the Apple Store or in the Google Play Store. I forgot to put the name of the app. But anyway, there's an app. It specifically converts the images into 星海乘风. I don't know why people do that, but anyway, there's an app. It's called Everfilter right, Everfilter. If you can search your Apple Store or the Google Play Store, you can find this app. But it is not as stable as the other popular ones. So, but anyway, if you want to do that, you can try this after, even right now. You can play with this app. It can convert the photos, the realistic photos, into the ones with 星海乘风. Okay. And the very last example of transfer learning or image manipulation is for the representation disentanglement. It's a very tacky term. I'm not sure is it any other easier way to understand this. So I think the better way is to show you examples that you would know what do we mean by representation disentanglement. And why do we consider that as an example of transfer learning as well? Again, I think many of you have played with this kind of app before, right? Face app. It can alter the images of particular attributes of interest. For example, this is the photo of the famous singer, actor, etc. It's Jin Cheng-woo, right? So you think his face looks very cool. So if we want to make him happier, yes, you can download this app, Face app, and change the attribute. Then you can convert his image into a smiling one. Okay, so you can imagine that previously we need to use like Adobe Photoshop. We need to alter, we need to edit the face images for like 10 minutes, 20 minutes in order to get this kind of examples. But now with the developed computer vision, deep learning algorithms or tools, we'll be able to do that in just a few seconds. Okay, so this is to alter the expression information of the face. What about the age? Yes, we can do that. We can make him older. And it also looks very practical, right? And it still looks handsome, even as an old guy. But anyway, so for this example, we want to transfer the face image from one age to the other. We just want to alter the age information for this case. So again, we are associating data information across two data domains, and here the domain of interest is age. That is the thing we want to focus on. And if you think he looks too handsome, old or not, you are not very happy about that, so you want to change his gender. Well, you can do so using this face app. It is how he or she looks like. It is how he looks like if he is a she. Okay, right. So you can alter his gender information from male to female, and that is how the face app will output the results. Again, it looks very realistic. It looks very attractive. And again, we don't need to use Photoshop or any other image editing software to do this for 20, 30 minutes. Again, with deep learning techniques. I know this company, they at least by the news release, they do say they use deep learning computer vision techniques to do this kind of style transfer. Okay, so you can see that we can do one-to-one or even one-to-many style transfer using deep learning techniques. You are doing manipulation or image translation across in different data domains, across in multiple data domains. Okay. So I'm not sure do we have time today to talk into the details in the last part, in the third part of the lecture. But anyway, one of the good things here is nowadays many people would think deep learning is like a black box, right? You throw your data into your learning model, you buy your GPUs from NVIDIA or buy any other hardware from any other companies. We don't want to anyway, okay. So you have the data, you have the hardware, you can make things happen. If you make things happen, if your deep learning model works, you are very happy. But if not, you do not know why, and you do not know what to do. Many people would have this kind of concern. With this research direction, this representation, this entanglement, it kind of alleviates or answers this concern. Because in this case, it will be able to identify which attributes in the feature, in your learned features, which of them are corresponding to expression, which of them correspond to age or gender information. So your learned feature is explainable. You will be able to explain the features, the deep features you learn. And eventually, with that, you can change the features you like. And that is why, for example, we can change the information from 1 to 0 or 0 to 1. Then we can manipulate the output image. We can change the attributes corresponding to age information. Then we can manipulate the face images with different ages. Okay, so it not only is related to transfer learning, but more importantly, it also addresses the concern I just mentioned. We want to be able to explain the learned features using deep learning models. I think that is also a very important aspect of this research topic. Okay, so hopefully I gave you enough examples, enough motivations, and see why we work on transfer learning. So for the remaining 30, 40 minutes or so, I will briefly highlight the settings, the scenarios of transfer learning. And I will use one particular task, for example, domain adaptation. But later we will go into the details. I will explain different settings if you have particular applications in mind. If you want to design your models, then you need to think about what kind of scenarios you are dealing with. What is your input? What is your output? For your input data, they are labeled or unlabeled. For your input data, for your input source domain data, they are labeled or unlabeled. For your input target domain data, they are labeled or unlabeled. I will go into different details for each setting so that you will have a better idea how are you going to design your own algorithm in the future. after you finish the class today or the course for this summer school. Okay, so the next few slides I will first highlight some existing examples techniques for transfer learning. So the first one is called instance transfer. Okay, so how do we do instance transfer in this part? So you can see that the source domain, we have the images taken by pictures. Okay. And for the target domains, we have the images, they are probably downloaded online. But, so anyway, we have the images captured by 2 different sensors. But only for the source domain, we have a large amount of labeled data. So if we are only dealing with the classification using this kind of images, then we can simply train our classifier using the training data in this domain, right? But for the transfer learning case, we need to identify, we need to recognize the images downloaded online or images captured by other kinds of sensors. So the thing is, if we do have the label information for such target domain data, what would you do? Well, if you have a sufficient amount of data in the target domain, the easiest way, the simplest way is train your classifier here, right? If you want to do recognition for this kind of data, and if you already have a sufficient amount of training data here, then you can simply train your classifiers here. You probably don't need to go beyond and borrow information from other places, from other domains, in case you borrow some noisy information, some irrelevant information. But what about in real life? You might only have a small amount of data for your target domain of interest. What about in real life, you only have a small amount of labeled data for the target domain of interest? So in that case, you still want to train your classifiers from the source domain. But at the same time, you want to identify which training data in the source domain which are relevant to the target domain data. For example, if you know these data instances that look like the computers in this in this data domain. So let me rephrase again. If you know that some data instances captured by the camera, they are the same type of objects of some data instances in this target domain, then you can increase the weight. You can focus more on this kind of data. So this is what we meant by instance transfer. So when we train our data eventually in the target domain, we can directly borrow those data points and put them together and train our classifiers. So that is what we meant by instance transfer. But you can imagine that in order to do this, we want to make sure that which data instances are important, which data instances we need to borrow to this target domain. So of course, there are some algorithms, there are some techniques behind this, but eventually the idea is the directly use of the source domain labeled data. Then we can put them together and train the classifiers in the target domain. We directly borrow the data from the source domain. Okay, this is probably the easiest way to do so. But in real life, you probably do not have the label information in the target domain. In that case, you would not know which data points are that do have corresponding information. In that case, you cannot do instance transfer. Or the other way is, in real life, you might have one feature describing the source domain data, but you have another feature describing the target domain type. in that case, you cannot put the data together to train the classifiers either. For example, if you use color information to describe your source domain data, but if you use shape information to describe your target domain data, in that case, you cannot do the instance transfer because you cannot put data together to train your classifiers, right? Okay, but anyway, so this is why I said this is probably the easiest one to do transfer learning. If you do have data, if you do have the ground truth information, if the data across two domains are described by the same type of features. Okay. So another type of solution is called feature transfer. So like I said, in many cases, the data across two domains, they are described by different kinds of features. For example, in the source domain, we might have images. So you can use sift, bag of words, or even use deep learning CNN type features to describe the images. But what about the target domain? What if we are dealing with text? What if we are dealing about spoken languages? So the features would be totally different across these two domains. So of course, we cannot do instance transfer to dealing with the transfer learning problem. What we need to do in most cases is we need to find a common feature space, like this gray area, this gray plane. We need to find a common feature space. So what is the purpose, or what we would like to see to happen in this common feature space? That means if we project the data of the same type onto this plane, onto this common feature space, hopefully the data of the same type, the data of the same label would be close to each other, right? For example, if we have images describing computers, if we have paragraphs, if we have sentences describing computers, laptops, hopefully after this feature mapping learning, after the derivation of this common feature space, we can project the data, images, and text onto this common feature space, and hopefully the data describing the same type of label would be close to each other. So why do we need to do this? Well, if we do find this common feature space, then we can project our training data onto this common feature space. Then we can train our classifiers on this common feature space, right? We can do classification in this common feature space. So the second way, the second solution to deal with transfer learning is to learn a good common feature space. And that involves the learning of the blue and orange arrows. That means the transformation functions for source and target domain data. And the objective function, the loss function, is the one I just described. We need to have the projected data of the same type. We need the projected data of the same label to be as close to each other as possible. That is the possible objective function you want to design in this case. Okay, but this is a more complicated case. So in the exercise today, we probably will not deal with this kind of heterogeneous types of feature. We will focus on image data only for the interest of time. Okay. So the third case is parameter transfer. The parameter transfer, actually, I think is a little bit similar to the first one, the instance transfer. The idea is, again, if we have labeled source domain data, we can train our classifiers, for example, SVM or whatever classifiers. And if you know, for some particular dimensions, they are more important, more informative, or more discriminated for the target domain data, then you will focus more on those particular dimensions. So this is so-called parameter transfer. I think we'll get back to some details later or some examples later. It is easier for you to understand the last part. Okay, so again, I have a table summarizing the settings and the general ideas different types of solutions of transfer learning. But again, I think we'll go into some particular examples or algorithms. The matter maybe it is easier than you can understand why some examples or some type of solutions, why it fits into some specific categories. Okay. So now for the next 30 minutes or so, we will look into the domain adaptation. It is part of the transfer learning. And why we look at domain adaptation? Because I think it is one of the most popular or commonly seen examples in transfer learning. So let me show you what is the definition of domain adaptation here. Domain adaptation means we only have labeled data in the source domain. For the target domain data, typically they are all unlabeled, or at least just few amount of them are labeled. So like the case I just gave you earlier, if we are dealing with domain, I should finish my definition. So the first thing is the data and their ground truth information. For domain adaptation, source domain, we do have label. Target domain, we typically only have unlabeled data or just few labeled data. And also a very important thing for the definition of domain adaptation is we are dealing with the same task across two domains. What do we mean by this? And that is why I want to go back to this slide. So this is an example of domain adaptation. We are always dealing with classification task. We are recognizing the computers. In the source domain, we have the image data from the cameras. In the target domains, we have the images online. But images from cameras or online, we are always dealing with image classification. We are always recognizing the computers. So this is what we meant by domain adaptation. We are dealing with the same task across two domains. And the most important thing is, usually, only the source domain, we are able to observe the ground truth information. For the target domain, for the domain of interest, most of them are unlabeled, or all of them are unlabeled. So this is close to real-life application as well. Like I said, you want to do face recognition, you probably don't want to always collect the data, annotate the ground truth information by yourself. You want to see if you can borrow some publicly available face data sets and use their label and train your classifier. Hopefully you will get some good features. And eventually you can just borrow those features to your data of interest. And that is just exactly the case of domain adaptation. You want to borrow the features you learn from one domain, and you want to apply that, after learning, apply that to the target domain of interest. Okay. Okay, so I just gave you the definition of domain adaptation, and not only the real life, the photorealistic images, also domain adaptation is very important to medical images, etc. Like the cases, like the examples I just gave you in the very beginning of this lecture. All right. So you think about if we are going to start working on transfer learning or particularly domain adaptation, how should we start? We are not working in big companies. We might not have many large data sets, large scale data sets. How can we start if we are in schools, in the university, or in some small industry or institutions? Well, there are few data sets which are available for you to start practicing your domain adaptation algorithms. The first one is the Amazon review data sets. So remember that in the very beginning, I gave you the example of semantic analysis, right? We want to learn whether or not the comment is positive or negative for DVD data. We want to determine whether or not the comment is good or bad for books, right? So that is the review data set actually available from Amazon. And you can see that there are different types of data domains. The kitchen, DVD, books, and electronics. So they do have the user comments, the reviews of different users, tons of users for 4 different categories. So like I said, the purpose of this data set is allow you to design your own domain adaptation algorithms and see whether or not you can learn informative features, whether or not you can learn discriminative representation from one domain to another, so that you can generalize your review models, your review prediction models for other domain types. So this is a publicly available data. If you want to work on similar problems, then you can go ahead to download this data set. It is publicly available. Okay. Well, if you are a computer vision person like me, well, you can go ahead and download this Office data set. This Office data set actually it includes 4 different data domains. One is Amazon, Caltech, DSLR, and webcams. So literally, they are the they are the object images captured by 4 different data sensors. Okay, and there are 10 common classes across these 4 data domains. So again, if you want to design your own domain adaptation algorithms, you can try. If you are able to learn good features, learn good classifiers from Amazon data, and once I give you the webcam data, even they are unlabeled during training, if you give you some unlabeled webcam data, whether or not you can use your features, your classifiers learned from Amazon data, so that you can do recognition of the webcam data. Okay. So not like the previous data set, this data set is purely for computer vision for classification purposes. But of course, because the raw data are available for the Office data set, so you can design any raw features you want to try. You can use raw data, RGB, but of course RGB would not work well for real-world object recognition. So you can design your own, you can extract your own feature of interest like back of words or even some CN features. Then you can go beyond and see, based on the use of existing features, can you identify the good feature dimensions to use? Can you design better models to do the transfer task? But anyway, again, these data are available, the raw data are available, and you can extract whatever features you want to use. Then you can go beyond and design your own domain adaptation algorithms. Okay, the third one, I've never used it, but it is a publicly available one as well. So it is also a real-world image data set, and you can see there are some overlapping between the Office data set because it also has the Caltech one, the ImageNet one, and also from other data domains as well. Again, this is the data for image classification, for object recognition, and again, you can use any existing features you want to design your own deep learning or domain adaptation algorithms. All right, well, so is there any, so I should say, are you all aware of bag-of-word features? Well, I think for the interest of time, I will skip for the next few slides, but because we will not go into the definition of bag-of-word features, so and because later I will talk about the deep learning part, so I think we can skip these few slides and come back if we have more time, or if we really need to talk more about the bag-of-word features. Okay, then the last part of the first lecture, I want to show you different settings of domain adaptation. Okay, we already know domain adaptation, we are dealing with the data across 2 domains, right? we are solving the same learning task across two domains. The thing is, in the source domain, we have labeled data. In the target domain, usually, typically, pretty much, we do not have any label information. But we are still trying to solve the same learning task. We are recognizing the computers. We are recognizing the books, etc. Okay, so that is the definition. That is the purpose of domain adaptation. So later I will show you some challenges or some settings for domain adaptation. So again, you can determine, you can think about what kind of features or what kind of applications you are working in the future. Then you will fit your particular needs into the corresponding category. All right. So what we really need to do, we need to address in transfer learning or particular domain adaptation. You can see I list 3 items. There are 3 things we need to conquer, we need to address in domain adaptation. So the first one is domain shift, domain bias. Remember that in the very beginning, I talked about the domain bias, the domain difference. We use synthetic data from video games to train our segmentation model. But eventually, we need to do segmentation for real-world things, right? So the domain gap in that case is the gap between the synthetic data and the real-world data. Okay. Data types, homogeneous or heterogeneous. But later we'll have more slides, like we are dealing with the same type features or not. For example, we are using bag-of-word features for both source domain data, or we have images in one domain or text in the other. So that is in that case, you need to deal with different types of data, and that is considered as heterogeneous domain adaptation. And the third part is the availability of the label information. But anyway, so let's look at the first one, the domain shift. The domain shift, like I said, we need to deal with the difference, the bias between the source and target domain data. And you can see that for different applications, for different topics of interest, you have different domain bias you need to deal with. But obviously, if you can determine the explicit domain bias of interest, that means that the task you are dealing with, it is somewhat easier for you to deal with. Because in many cases, you are dealing with, like, another example is also for the road scene segmentation. Didn't we just mention the road scene from Frankfurt and the road scene for Taipei, right? In that case, we also have domain shift. We also have domain bias. But it is really hard to describe or determine in explicit words or in physical terms what the domain bias it is, right? But anyway, so I just show you some examples for each particular examples or applications, what domain shift it corresponds to. Okay, so that is the first thing you need to deal with in transfer learning or domain adaptation. Well, before the rise of deep learning, people have already been working on transfer learning or domain adaptation. So the first thing I want to highlight, you probably will not see this in some deep learning models, but anyway, some still do. And people use this before even the use of deep learning. So the first technique to address the domain shift is the calculation or the minimization of the MMD. What the MMD stands for? Well, it is maximum mean discrepancy, but reading out the definition doesn't help, right? So anyway, actually in this case, looking at the equation, that is easier for you, for all of us to understand. What the MMD calculates is the difference between the means of each domain, right? Because for the first term, you can see that we sum up the features, we sum up the data in the source domain. The subscript S indicates the source domain. In the second term, we also sum up the data in the target domain. And the subscript T represents target domain. And we simply calculate the difference between the data means, the domain means. And for the MND, obviously, when we want to alleviate, disregard the domain bias, we want to minimize or maximize this term. We want to minimize this MND term. So you can see this is a very straightforward, simple example, simple idea to deal with domain shift. We just calculate the mean from source domain. We also calculate the mean from the target domain, and we try to make the gap smaller. We just make the domain, the entire distribution, the mean of the entire distribution to be close to each other as possible. And you might ask what this phi stands for, right? So remember that in one of the previous slides, we do have the orange arrows and the green arrow, right? Like this one, or blue, okay. So phi indicates the transformation. You want to transfer the data, you want to convert the data from the original domain to the common feature space. So phi indicates the transfer function or this transformation. So you can see that if we use MMD to deal with the domain shift, basically we are determining the green, the orange, and the blue arrows, and after mapping the data into the common feature space, we want the data mean to be close to each other. So that is in the MMD. But if you have learned SVM or some nonlinear classifiers, of course you know you not only can calculate this kind of distance, this kind of things in the original feature space. You can use kernels. You can use kernels to calculate these things in higher feature space, in nonlinear space, right? So anyway, so this is the technique before the rise of the deep learning. You want to project the data into a common feature space. You want to make the global means to be close to each other as possible. You can do that in the original space, or you can do that using kernels to do this in the nonlinear space. Okay, so this is the first technique to deal with the domain shift. But later, using deep learning parts, we will see more variations, more variants of the learning techniques to deal with the domain shift. Okay. Then the next challenge is also I just mentioned the homogeneous and heterogeneous domain adaptation, depending on whether or not we are dealing with the same types of features or different types of features. So this example shows the homogeneous domain adaptation. We are recognizing the photos. The source domain are the images captured by the cameras. And the target domains, we have the images downloaded online. So they are all images anyway. So if you use bag of words, if you use CN features, you can do so. So the data from either domain, they are described by the same types of features. So if you are dealing with this kind of transfer learning, if you are dealing with this kind of domain adaptation problem, they is considered as a homogeneous domain adaptation task. So remember that, like we just mentioned a few minutes ago, if we have different types of data, if we have data described by different types of features, like one is image, the other is text, and in that case, if we still need to associate the data across these two domains, then this is so-called heterogeneous domain adaptation, because we are dealing with distinct types of features. And that is why we said this is a heterogeneous domain adaptation. Okay. Well, in the definition of domain adaptation, there are two things. Remember, one is we are dealing with the same task, the same learning task across two domains. What is the second definition, or the commonly considered requirement or assumption in domain adaptation? Remember, in the source domain, we have label information, right? What about in the target domain? In the target domain, we typically assume that there's no label information, or only there's a small amount of labeled data in the target domain. So that is the assumption, or at least the commonly used requirement for domain adaptation. But you can imagine that for homogeneous information, it is pretty much an easier task to do domain adaptation, right? Because they are all images anyway. They are data of the same types of anyway, right? What about heterogeneous domain adaptation? For heterogeneous domain adaptation, because the data are totally different, they are described by totally different types of features. Like one is CNN, the other is like some word embedding features. So the data distributions are very different. The data dimensions are very different. So in that case, if you do not give any label information for target domain data, it will be extremely difficult for you to deal with the domain shift. Okay, it is understandable, right? So for heterogeneous domain adaptation, usually we still require at least a small amount of label data in the target domain, so that when we learn the common feature space, we have some clue to follow. We have some information to exploit. At least we have some label information, just for few label data in the target domain. So for the heterogeneous one, typically we do not deal with unsupervised setting. Okay. Although some people start to work on this challenging topic, but anyway, as you can imagine, for the heterogeneous domain adaptation, because the data are so different, so usually we still assign some label data during the training process for the target domain data. Okay, so the second challenge for domain adaptation is the feature type. What about the last one? The last one, the last one is the label availability in the target domain. So like I said, if you already have label data in the target domain, you probably do not need to do transfer. You probably do not need to do domain adaptation. If you already have a sufficient amount of data in the target domain, you can simply train your classifiers. You can simply extract good features to use. But sometimes if the target domain data, the scale, the number is not large, then it might be a good idea to look for help from other domains. So we still can do domain adaptation. So since you do have the label information in the target domain, so that would be considered as supervised domain adaptation. Okay. Then we go up for some examples of supervised domain adaptation. Like these few examples, this is so-called person re-ID, person re-identification. You would see this in lots of surveillance applications. What do we mean by person re-ID? That means given a camera pair or given multiple cameras, you need to determine whether a pair of images, they are of the same person or not. So that is the definition, or that is the topic of person re-ID. Okay. So during training, typically, I will give you a large amount of data across 2 cameras. And I will give you the label information. So in that case, you can consider that as a supervised domain adaptation. You want to convert, you want to transfer the information from one camera to another. So you are dealing with transfer learning. Even the label information is available in both domains, for both cameras. Because eventually, for the goal of person re-ID is when I give you a pair of data, you need to tell me whether or not they are of the same person. This is commonly seen for like people tracking or some surveillance purposes. So this is person re-ID. Another example for supervised domain adaptation is for this action recognition across different camera views, right? Because in many cases, you will set up the cameras. You want to determine whether or not people are fighting, whether or not the order is failed or not. But you would have different kinds of camera views. So again, in training, I might give you a sufficient number of training data. You know which cameras they are from. You also know the ground truth information. But the thing is, eventually, you still need to determine, you need to do recognition of particular action, whether or not, doesn't matter which camera images I gave you. So that is the case. Other supervised settings like sketch to photo recognition, infrared to photo recognition, those are cross-domain recognition, dealing with cross-domain data. But during training, you always have ground truth information from both domains. Okay, so this is a supervised setting. And the next one is semi-supervised setting. And as you can imagine, for the semi-supervised setting, that means for the source domain data, we always have label information. But for the target domain data, in this case, the same example I just gave you earlier, for the target domain data, they are text data. But we only have ground truth information for some of them. We only know these two paragraphs, they are describing the computers. For some other paragraphs, we do not have the label, the ground truth information. But for the source domain data, for the images, we do know they are computers, they are bicycles, etc. So the semi-supervised domain adaptation is this kind of setting. We have labeled data from the source. We have partially labeled data, we have partially labeled data in the target. So how can we learn a good feature space given this kind of setting? We need to exploit the information from the remaining unlabeled target domain data. So anyway, this is so-called semi-supervised domain adaptation. Yeah, and they are different. Of course, the most challenging one is unsupervised domain adaptation. So imagine that if we are dealing with images like the computers from the cameras and the computers from online. For this kind of case, if we do not assign any label information for the target domain data, then that is the most challenging case, the unsupervised domain adaptation. We can go back to some variants if we have time. But anyway, so the last one is imbalanced domain adaptation. What do we mean by imbalanced domain adaptation? For example, we have we have 3 different categories in the source, but eventually in the target domain, we only have like 1 or 2 class of interest in the target domain. So in this case, we not only need to deal with domain shift, we only need to determine which class are of interest when we transfer the information to the target domain. Because you can see the classes of interest, they are not equal across 2 domains. That happens in real life, right? For example, in real life, you just want to recognize dogs and cats. But in real life, you go to the ImageNet data, you have tons of categories there. You do not want to borrow the one, you do not need to learn everything from the ImageNet data. You just need to transfer some information of interest to the target domain. So that is the imbalanced setting of domain adaptation. Okay, so I think this is pretty much it, and I think it's a good point to take a short break, because I think later we can talk about some deep learning techniques to deal with transfer learning and domain adaptation. So do we have any questions so far? Okay, so let's take a 30-minute break.